All right, good afternoon. It is 3:05. I saw someone looking at their watch, so we're going to get started. So it is my pleasure to welcome all of you to the 2024 Hoyt C. Hottel Lectureship. And before I introduce our distinguished speaker for the afternoon, I'll say a few words about Professor Hoyt Hottel, after whom this lectureship is named. Hoyt Hottel came to MIT from Indiana in 1922 at the age of 19, having just received an AB in chemistry from Indiana University and never left. I do encourage you to leave and come back. You can come back, but leaving and coming back is good. He got his SM in chemical engineering in 1924, studying under Professor Walt Whitman, who's a former department head for chemical engineering, and then served as a practice school station director in Buffalo, New York in 1924 and 25, before coming back to MIT as an institute fellow in fuel and gas engineering, and then being appointed as an assistant professor in 1928. He was promoted to associate professor in 1931 and full professor of fuel engineering in 1931 and full professor of fuel engineering in 1941. In 1965, he became the first Carbon P-Dubs Professor of Chemical Engineering, a title he held until he transitioned to Professor Emeritus in 1968. He remained active in the department until his death in 1998 at the age of 95, and was a central figure at MIT, particularly in this department, for more than 75 years. Professor Hottel is remembered for his intensity, his intellect, and his integrity. His lectures aim to make students think. He made seminal contributions to the measurement of gas emissivity. He established the mathematical framework for the quantitative treatment of furnaces, conducted the first systematic investigation of the laminar to turbulent transition in diffusion flames, and explode heterogeneous combustion. Professor Hottel was co-founder with Bernard Lewis and A.J. Nerid of the Combustion Institute. He was elected a member of the National Academy of Sciences in 1963, the National Academy of Engineering in 1974, and the American Academy of Arts and Sciences. Additional professional honors include the U.S. Medal of Merit, the Founders Award from the National Academy of Engineering, and both the Founders Award and the William H. Walker Award from AICHE, and those are just a few of his many honors. Hottel's broad interest in energy is very relevant to today's energy, sustainability, and climate discussions. With funding from Godfrey L. Cabot in 1938, he organized the world's first solar energy utilization research center. Those studies led to the choice of the flat plate collector as the most promising device for solar heating, and construction of the first solar heated house, along with 3 others, which provided data for economic assessment of solar space heating and hot water supply. Professor Hottel advocated for the logical assessment of the economic use of the sun as an energy source. And so certainly today, as we think about, again, sustainability and going towards carbon-free energy, it's very interesting to think about the foundations of that research being done in this very department. And now to introduce our guest today, Dr. Jefferson Tester. Jeff is professor of sustainable energy systems in the Smith School of Chemical and Biomolecular Engineering at Cornell University. He also serves as Cornell's principal scientist for Earth Source Heat. Professor Tester founded and served as director of the Cornell Energy Institute from 2009 to 2017, and is a fellow in the Atkinson Center for a Sustainable Future, as well as a Kroll Energy Fellow. Now, we prefer to think of his years before 2009, because before 2009, Jeff spent over 25 years here at MIT with us, where he served as director of the School of Chemical Engineering Practice, also known as the Practice School, from 1980 to 1989, and also as director of the MIT Energy Lab from 1989 to 2003. While he was here at MIT, he led a highly influential study of the geothermal potential of the United States, resulting in a major report published in 2007 called The Future of Geothermal Energy. Professor Tester was the U.S. representative for geothermal energy to the Intergovernmental Panel on Climate Change, also known as the IPCC Working Group. And in 2011, he received the Special Achievement Award from the Geothermal Resources Council. In 2021, he was elected to the National Academy of Engineering. And so we have lots of photos of Jeff because he was with us for many years. You can see in the upper left, that is Jeff receiving his PhD from MIT in 1971. In the middle there is him as a station director. To the right of that is Jeff working on the Sustainable Energy textbook, which is one of his contributions. That, by the way, is the Lewis Room, 66360, which none of us would recognize from that photo. Jeff was very, very well known for going on bike trips. So if he ever says, hey, do you want to go for a ride? Unless you're committed to 50 miles, say no. And then the last picture there is perhaps Jeff's most famous student, Rocky Jones, who made several appearances in his seminal textbook on thermodynamics. So with that, please join me in welcoming back to MIT, Jeff Tester.
Everybody should hear me now. Is that good? So that was, if that's a short introduction, Professor, that was much too kind. And you covered a lot of the ground I was going to say about Professor Hottel because I knew him. But I'm probably one of the few people in this room that actually lived at his house. He was on sabbatical, and I was just newly here for a short period of time to teach a course for a semester before I went off to run the practice school station in Oak Ridge. And he needed someone to kind of mind his house when he went to Australia. There might be a few people in this room that remember that. If you ever want an experience of what it's like to live with someone like him, try living in his house at that time, because the entire tour of the place had a lot of interesting stuff in it. For one, he had to show me his cylindrical slide rule. Most of you people in this room don't even know what a slide rule is, but a cylindrical one is really awesome. Had to be in temperature-controlled conditions, and you have enormous, because of the circumference, enormous resolution of this. And then, of course, his multi-fuel furnace heating system in the house. He said, now, Jeff, you've got to be careful. If the oil price is too high, we're going to switch back to coal. And if we can get gas in the house, we'll switch to that. So needless to say, we did it all with oil. Because it was too complicated to figure this out economically at the time. But at any rate, it's quite an honor to be here. And I was actually with Professor Hottel near the end of his life, and he was still incredibly active. He got interested in some of the stuff that we were doing on reactions in supercritical water, was very interested in combustion, of course, throughout his life. And that work on solar energy actually came back to help us at a number of times. I looked today at one of the original papers. 1942 was the first paper, and still stands today as a definitive example of how you should do essentially thermal energy exchange with solar energy. So you can do things even without a PhD in this department and succeed quite well. But on the other hand, I'm going to share with you some things today. I feel like I should be talking about 1040 in this room. So I spent so many years doing it, but I will spare you that. But I thought it would be interesting to kind of give you some history behind how this became an interesting thing to work on as a chemical engineer, and how it really matters in terms of the kind of impact you might have in work you do in kind of a team effort. So do we have to have this light on? Because there's going to be a bunch of maps here. Is there a way to control that? There's got to be, right? If I hit this, start to hit a button or two, don't touch those, right? Yeah. There we go. Okay, much better. Okay. And, okay, so let's come around here so I can see you a little bit closer. So these are topics, and we're going to go through a lot of these very quickly. And then eventually I will talk a little bit about what we're doing in the area of research to show you how you can apply pretty fundamental engineering research to kind of help out with some of the problems. And then I'd like to get back to the real practice of how this is being done on campus itself, with drilling a deep well as an exploration well to start with to 10,000 feet or so, and then trying to figure out how we pay for it all. So there's been a lot of people involved with this. I mean, rarely do you see a kind of a team that involves not only faculty members and students, sort of the common thing in postdocs, but members of the facilities as well. And a lot of them were trained engineers, and they were very excited about what Cornell was trying to do in decarbonization, and it led to a different kind of engagement. Lots of scientific papers were written, but lots of reports, and dealing with a lot of fundraising involved with both agencies as well as the state and federal agencies, but also other people on the Cornell campus to make a commitment to help fund this thing. So I'm going to try and give you some reasons why this might be important. And a lot of you, I'm sure, have seen these maps before, but if you look at where we live and where half of the country is in terms of the northern tier, these are really, really major zones for heating. And if we start to look at heating degree day as a unit which kind of looks at how many days do we have to actually heat above a normal temperature of, say, 70 degrees Fahrenheit or something like that, you might be surprised to remember that most of you probably have the idea that Reykjavik's in Iceland. Ithaca, New York has actually more degrees heating days. And you'll keep that thought because they heat all year round in Iceland. We only heat, roughly 9 months a year or so, but we still have huge demand at certain times. They have moderation due to the Gulf Stream and things like that. So Ithaca gets some very, very cold days. So you have to keep that in mind as well. So about when I first left here and went to Cornell, this is something we tried to do for a number of years. And there was an MIT undergrad who came to grad school there, and he said, I think we can tackle this thing. So we started to look at not only where energy is used, these are different sectors where it might be used, and this is all thermal energy now, not electricity directly. And then we started to think about what is the actual temperature at which it's used at, as opposed to the amount of energy, just in terms of that category. So we can plot now energy demand here. This is in a unit of an exajoule. If you're not familiar with joules, you're in trouble if you're in this room. But an exajoule is 10 to the 18th joules. It's roughly 10 to the 15th BTUs if you want to make that transfer back to about 1,000. We use 100 of these a year as primary energy in the U.S. So if you're on here in a scale of 10, that's 10% of the U.S. energy demand. And think about this. This whole area here is, a few degrees effectively above room temperature, and you know where that heat comes from, primarily from burning fuels. So if you started to integrate those bins there below, say, 100 degrees centigrade, you come up with about 20% of U.S. energy demand. Now, this is not to say that electricity is important or transportation fuels, but this is almost neglected if you really want to get to low temperature, low carbon intensity and things like that. You've got to look at the low temperature spectrum. And we certainly have to transition from this if we're going to get rid of carbon. So how do you look at this? Well, we broke this down in other ways because we wanted to convince people this could have a big impact. So we looked at where are the carbon footprints. This is the use of low temperature heat demand versus electricity. This might surprise you because if you look at our states in New England and New York, they're using more heat than they are electricity. We'll worry about the, how you scale this thing, but in terms of how the actual value of it is significantly different. And if we go to other states and look at the carbon footprint, you have to be careful here because this is per capita. There's only a few people living in Wyoming, so you don't have to worry too much about it. But look at New York over here. Very, very low carbon footprint per capita. And the reason for that is their electricity load is low, and we have no coal plants anymore operating in New York State. And a lot of hydro and several large nuclear plants. So the carbon footprint of electricity generation is low. And you compare that with, for instance, West Virginia, which is going to burn probably the last ounce of coal they have in the ground and still try and transform to low carbon as well. So they'll do it in different ways. So that's one thing that might get us interested. The other is, if you start to look at across that northern tier, 20 to 40% of the carbon footprints from heating. 16 of these states, and I'd be willing to say there's a good portion of them that are red states and blue states, it doesn't matter, they still have aggressive goals to decarbonize. And they want to do it quickly, roughly to get not only cover their electricity, but cover 80% or more of their energy use in the next 30 years. These are goals. They're not necessarily achieved things yet. The state of Massachusetts certainly has that. All the New England states, certainly across that northern tier. And we obviously have to do this in an affordable, accessible way. So that sort of sets a stage for this. So The question you might ask, is this an option for geothermal? There's a lot of geothermal power produced in the world, and some of it's used for heating as well, and not just electricity, but not in the U.S. So these are the three ways, if you aren't familiar with geothermal, we have to have a little bit of a primer here. You can make the electricity. If you do that, you have a big challenge because geothermal resources aren't really high temperature. They're not anything like coming in a combined cycle, not at 2,000 degrees. They're more like at 200 or 150 degrees C. So the efficiency, the thermodynamic conversion efficiency is inherently low. So if you take 100 units of geothermal heat out of the ground, you maybe get 10 units of those back as electricity. That equation changes if you either do it with heat pumps, where you'd have a finite positive coefficient of performance, or if you do it with direct use. So it changes the economics a lot, and it actually is important if we're going to look at transitioning to geothermal heating. So here's how these systems work. You need a few ingredients to make them. First of all, they have to be accessible by some level of technology, usually drilling, and we have to get to sufficiently high temperatures or it's not interesting. So that means you have to look at the country more broadly as to where those high temperatures might exist at certain depths. The most important part, and this gets into the area of fluid mechanics and heat transfer, you need to have a well-connected system between an injection side of it and a production side of it, where you get a lot of contact with water being used as the heat transfer agent to extract that energy efficiently, because you're paying a lot for those wells, big capital investment, and they have to last for a while. And so in terms of flow, you need to have them last long enough. So it can't just be for a period of a year or so. The kind of investment that's going to be made is going to be in a year, 10 to 20 year horizon with any kind of reasonable discounting rate or things like that. So that's something to keep in mind. High flow, lots of contact with the rock surface, and then ultimately you need to be able to use it. This is a typical geothermal power plant. This is located in north of San Francisco at the Geysers Field, big famous field in the northern part above San Francisco, about 100 miles from San Francisco. This is another plant that's actually in Reno, Nevada. Some of you I know have been there. We were talking about that last night. All the electricity in Reno comes from geothermal. Surprising fact. In the early days when the Geysers Field was going, about a quarter of all of San Francisco's power was being generated this way. It's not quite as big now. San Francisco has grown, and this has been depleted partly over time, but it's been in existence for about 50 years or more. And so now, if you don't have those four ingredients that I just showed you, you got to think about what are you going to do? Are you going to give up on the fact that nature hasn't been kind to you? So you transition to what's been known now, and it has another name. It used to be called hot dry rock. It's now called enhanced geothermal systems, or EGS. I like to refer to them as engineered, because that E means a lot more than just enhance. It means you really have to intervene in this in some way. So you're essentially creating a reservoir that sort of emulates the conditions that you'd have in a good natural system. So you kind of know the right answer in terms of productivity and lifetime, and you're going to do it with multiple wells. But you have to be able to prove that that's going to work. So it involves the same sort of methodology you'd have for oil and gas exploration. You do an exploration well, you do an early scale up, you try to do assessment, make sure the reservoir works, and then you scale up to whatever you need. And that's what we're trying to do as well, as you'll see at Cornell very shortly here. There's one critical question that you have to worry about technically, and that is, and this is primarily through all of geothermal systems, not just these so-called EGS systems. You have to have enough productivity and lifetime, and that means that you have to be in contact with a lot of rock surface area and a lot of volume of rock. The volume is providing the storage of the energy. This is very different than solar or wind. You're essentially extracting energy that's already in place in the earth, and you're trying to use it in a sustainable manner. So this represents kind of the volumes and areas you'd be talking about. A cubic kilometer of rock and 1 million or so square meters of effective heat transfer surface in that. So there's different ways to look at this. This is a picture of microseismic events that were taken at a site in France, right on the German-French border, by an EU-funded project several years ago. And the important thing to represent here is the scale of this. This is 1,000 meters. These are not earthquakes that cause damage. These are just small earthquakes. And if you're familiar with the Richter magnitude, maybe starting at a -4 Richter, going up to maybe 1 or so. So they're not damaging property or endangering people, but they're giving you an ability to actually monitor the reservoir and to see how big it is. Whether or not, and these were three or four different stimulations that were done, so-called hydraulic stimulation. We could use the word fracking, but it is different than the same kind of technology that you use for oil and gas. And if I think this isn't going to work the way I thought. Maybe I can get this to work on. Let me go over here. We can rotate this picture around so you can see there's structure to this as well. Oop, not working. Well, we had it working before. Maybe, there we go. Okay, so if you look at this, it's not exactly spherical either. So part of the reason why these so-called fractures may open up is against what the existing stress field is in place. And so that has directionality to it. And typically, you view that the fractures that would be reopened or created would go perpendicular to the least principal stress that you have. So you have to understand stress, you want to understand the rock fabric, and you want to make sure you know how this thing is operating so that you operate it safely as well as productively. So what that takes me back to is thinking about where are the good systems on the Earth, or in the US in particular, around the different parts of the world. And so we came up with this simple diagram several years ago. We actually had this in that report that Professor Prather was talking about. And so we took some liberties here. It's a two-dimensional plot of multiple dimensions here, but this is gradient here. This is the average temperature at which the Earth's temperature increases with depth. So you take whatever you have at a given depth and you just divide it by the total depth and the temperature increase over the surface temperature. And this is an arbitrary scale of permeability, which I'm going to say is something that represents connectivity, because connectivity is what it's all about between an injection set of wells and production set of wells. And then ultimately, if you're lucky enough to have a lot of fluid content, you could kind of say that must sort of qualitatively at least scale with porosity. So if you look at the high grade section over here, this is where you'd have a lot of connectivity, high natural permeability, and a lot of fluid present, and most likely a high gradient. Okay, so you ask the question immediately, well, it says I need temperature, I need permeability, and I need sufficient hot water or steam. Don't always have those, so that brings us to this EGS sort of hot, dry rock sort of vision of what we might do. So let's take a look at the US, for example. These are temperatures at a given depth of 4.5 kilometers. It's a little bit deeper than we drill, but it shows a little more structure than you can if you just go shallower. So you know where Ithaca is at this point. If you don't, you will after this talk. You know where you guys are. So you can see here that this is in the range of 100 to 125 degrees or so, hot enough to be providing direct use for heat, not very good for electricity at all. And this structure here is the Appalachian Basin. So if we were to go down to our friends down in West Virginia, you can see they have a lot more higher temperatures there. And so they could get to those higher temperatures, maybe for electricity as well as for heat, but they also have a slightly different approach than what we're trying to take up in Ithaca. And some other features on here. This is Yellowstone National Park over here. We're not going there, but it's just to give you an example of how hot things can get. And again, you're looking at a pretty recent volcanic region. This little red dot here is the geysers field up at north of San Francisco. So there are good examples of high-grade resources in the country already, some of which, and most of the power plants are in this part of the country, which you'll see soon. So we come back to this diagram and you say, well, where are we? You know, where's Massachusetts and where's New York? Well, there's Iceland. We don't have to convince you of that. If we were in Tuscany in Italy, we'd have the same thing, or in New Zealand. There's lots of places like this around the world. Not big enough to kind of capture the demand that we have in the US, but this is what a lot of the country looks like, which is up here. So usually when you show this to people who are funding things, they say, well, it's very nice, Professor Tester, but we can't fund that because that's just a too low grade. But if you start to change the equation, start to think about heat, it changes the economics significantly. So we're dealing with gradients in New York, and they'd be very similar here. of about 25 to 30 degrees C per kilometer. So if you go 3 kilometers, you're going to get something in excess of maybe 75 degrees. We're about 85 or so in the current hole that we drilled. If we were going to Iceland that deep, we could even get extremely high temperatures. But we also might not have any permeability, and we might not have any natural fluid present, or very little. So we have to somehow function in this big EGS space here, figure out how to make it work. So if you come back to this and sort of say, okay, here's the U.S. electric power. We're the largest producer of geothermal electric power in the world. That may not be true for very long because Indonesia and the Philippines are rapidly growing their potential and developing power plants. And some of the bigger ones are shown here. I think you should recognize that a lot of at least the congressmen and senators from Nevada think of their state as similar to very high-grade geothermal, lots of small geothermal power plants. There's the geysers field, but look anywhere east, and there are virtually no electric power plants. But we have all of this potential need over here due to these two things sitting on that side. So the heating demand is large in the northern tier states and currently met by fossil fuels. So if you view this as an opportunity rather than a liability, if you're going to do carbon neutral district heating in the north, the place to do it, of course, would be in this region here, because you don't have much heating over here anyway. So it makes sense to go where the demand is and maybe where you have access to it. So if we return to this graph for a minute, here's what we showed earlier. Large heating demand, so it's much more than just a story about what we could do at a given campus or what we could do in the state of New York. It applies equally well to, I think, what the goals might be in this state or other states in that northern tier. And so hopefully demonstrating something at full scale might be the kind of catalyst that can make things really happen. So here's Cornell. And so one of the things that happened before I decided to leave here and take on a new challenge was that the president of Cornell at the time signed an agreement with, I'm not sure exactly who, but I think it had a lot to do with the American Association of Universities to essentially decarbonize the entire campus, the entire energy domain. This included everything, not just heating, electricity for all the power needed, as well as transportation, a huge, Cornell people like to get in airplanes just like we do here, so that's really tough to do. Pretty tough to do it with electric airplanes. So you have to think about how you're going to get there. So we were working primarily on the heating demand. You'll see a reason for that in a minute. So one of the things is look at the energy demand. This is a given historical record of annual energy demand at Cornell. The red bars here are heat. The green bars are electricity. This is in millions of BTUs per year, but this is a million, so it's a big number. We'll show you in megawatts in a minute or so. And chilled water is the cooling that's provided to the campus. We have actually a few weeks of summer, but it's not quite that bad, but there is a significant cooling load. And then this sort of darkened area in the back is the amount of gross square footage in square feet that the campus has. Like MIT or like any other campus, huge amount of growth over those number of years. This is 23 or so years. There's a lot more buildings here now. They have obviously heat demand. Same thing is true in Ithaca. But what's been remarkable is that the facilities group has been able to keep the total, which would be the sum of those 3 bars, actually slightly decreasing. So they've been incredibly aggressive with energy efficiency, retrofitting terribly old buildings in the right way and building new buildings that are much more efficient. But yet, we still have this high demand. And the heating part is still the biggest part of this. So if you start to break this down, this is a typical year, and this gets to the point I was making about these really very cold days. So what we're looking at is megawatts thermal now. That's a unit we should all be more or less familiar with. Cornell has a load of electric, sort of steady state. We have a synchrotron on campus and a few other things. Lots of students that leave their lights on all the time, and a lot of animal control areas that have a lot of electricity use as well. So that's about 30 megawatts electric. This is the heating side. And if you were to just estimate, maybe the average would be somewhere around 50 or so if you tried to just integrate under that. But look at these several cold days. And this is just one representative. This is going over 100 megawatts thermal. So if you're an energy designer, you want to make sure I can cover it all, especially if you want to decarbonize. But you might not want to do it with an over-designed system because you're only going to use it for 20 days. So it brings in this idea of an energy system approach where perhaps, and you'll see it in a moment or two, we can use biomass, particularly waste biomass, as a source of peak heating because it can't supply it all, but it might be a perfect fit for this. So if we started to look at the peak demand and integrate under this curve, this is, we're really talking about having the ability to only have about 3% of the Cornell total demand if we were to have that 50 megawatts of baseload. There are a number of things that are done here to save energy. We use local energy storage. The entire campus is being, significant amount of it's already converted from steam to hot water. Very old transmission and distribution in place when they were just burning coal. But they've transformed that to much more high efficiency, a lot less heat loss in the ground. There's hundreds of kilometers of buried pipe just delivering hot water. We also take care of this with the idea of using biomass and thermal storage that I'll show you in a minute. And so you could get down to a much lower level here, especially taking care of this peak demand in here with storage and biomass. So here's some of the things that they've done. And I think this is pretty remarkable when you look at the time of this. So lake source cooling, which provides all the cooling for campus. We have a deep lake nearby. It's got a couple of trillion gallons of water in it. It's cold at the bottom. It's 50 miles long. And so Cornell takes advantage of the cold temperatures at the bottom with a very efficient lakeside, lakeshore heat transfer operation, and then transfers that to a circulating loop to the campus to bring it chilled water. It's about 38 or 39 degrees Fahrenheit, just a few degrees above the freezing point at the bottom. Was put in place long before anyone was ever worried about climate change. This was done to get off of using refrigeration because they were worried about the ozone depletion effect of the freons that were being used. So had another reason, but it was also the best economic choice. Cornell totally invested in it. This is a 48-inch pipe that goes down off the campus, a huge investment of money on the totally spent by Cornell, no outside thing. They also transitioned from coal to natural gas about the time when I left here, a little bit after that. And that changed things. It's a very efficient combined cycle plant. Still has a carbon footprint, but much better than coal because they could produce all the electricity and take care of the heating. So it dropped the carbon footprint, but not to the level they have to get to. They've had a hydro plant in operation for over 100 years. They've upgraded it, but it's still tiny compared to what the electric load. Electric load's 30 megawatts, so it's a portion of it, and it's obviously carbon-free. And they recently, and up to now, I think this number is even bigger, we've installed on Cornell property 28 megawatts of peak solar capacity. So on a really, really clear day, which doesn't happen too often anywhere, you can probably take care of the electric load. But in the winter, when the sun's not out, you've got to have another alternative. So the longer-term seasonal aspect of this says, well, maybe wind would be a better choice for this. And so they're in the process of doing this. But there's a lot of issues associated with public acceptance of wind, believe it or not. Lots of NIMBYism still around. Solar, for some reason, which takes up a huge footprint, doesn't seem to bother as many people. But there's negative parts to any kind of development or deployment. So that's underway, and that obviously will have to become in place. This is also a New York State goal. They're beginning to recognize that the sun's not out in the wintertime at all, hardly, and it's not out at night anyway. So they're going to have something to take up. But this is the part that we'll get to show you. There's not too many schools like this that have a big heating load and have a lot of potential for agriculture waste. We have 20 dairy cows at Cornell. They produce a lot of milk and other good things for us all to eat, Cornell ice cream and things, but they also produce a lot of manure. And if it's not managed right, it becomes an equal environmental issue with methane emissions and the fact that it also could lead, if improperly done on larger farms, to eutrophication and algae buildup in some of the river basins and lakes that we have in the area. So this leaves geothermal as the last, and we're kind of thinking of that 50, if you just think about that 50 megawatts thermal, that could take care of the base load demand and how we could go about doing it. So here's the the kind of conceptual concept in a cartoon. Over here we have the lake source cooling, the hydro plant. This is the Cornell campus with its district heating loop already in place, being upgraded to low temperature hot water. And we have a power plant, obviously, that is now all gas, very efficient to provide both heat and power to the campus. And we're indicating conceptually this might be the sort of way in which we would deal with gasification, but it's probably not going to be done completely thermally to start with. If we do it, there are lots of options for this. We would probably do, and I'll show you in a minute, anaerobic digestion followed by some hydrothermal conversion, but take advantage of the wet biomass waste we have from this dairy manure, which is produced 24/7 for sure. Bunch of solar collectors, and then this is the concept for the earth source heat program. And we'd be talking about temperatures in that 80 to 90 degrees C, and at about a depth of about 10,000 feet, or 3 kilometers. And if you start to go back to this, you might ask the question, well, why would you do this? Well, we have accessibility for sure. There's no you can drill to these depths very easily. We happen to have a huge development of shale gas in Pennsylvania, a few miles. It's outlawed in New York State, but it's just 30 miles or so from campus, where a lot of infrastructure with the right capacity drill rigs and know-how to actually do the drilling. The idea would be that we have to develop at least a 2-well system and prove that this thing works before we would scale it up. So that's the stage we're kind of at now. And then producing hot water at this sort of rate of 20 to 50 kilograms per second in that well pair to kind of achieve the kind of levelized cost that we're going to need to make this work, and lasting about that period of time. We'll get into the specifics of this in a little bit. And then ultimately we have to way to utilize it, which we of course have with the district heating in place. In a lot of places you don't have that district heating infrastructure, so that would be additional capital costs. But in Cornell's case, they have it already, so it's a logical place maybe to do this. So the way is baseload or source heat, geothermal. This is Cornell's name for this. Centralized heat pumps, we'll get to the reason why we want to use that. These are really supercharged heat pumps that have very high coefficients of performance. And then waste biomass for the peak heating side of it, which I'll show you in a minute. So why is Cornell interested in this? Well, there's a campus commitment to do this. The university set the goal, not us. This probably came initially from the students and then up through the president's and provost's office. And surely many of the faculty were in favor of this, but it involved a commitment which isn't usually made at a university campus. And the time frame for this started with 2050, and then everyone pushed hard to get this back to 2035. Well, we're still at 2035. It will be remarkable, let's say, if we could actually do it all, but getting that kind of goal in front of you really helps generate interest and the financing for it. We have a lot of proven experience of the facilities group building a power plant on campus, doing lake source cooling, lots of committed engineers on that side of it. The faculty and facility staff expertise in both geothermal and renewable energy technology is there. An earth sciences department at Cornell is embedded in engineering. It's not a separate part of the Arts and Science College. That's a little bit unusual. And And finally, the concept of this is to kind of have a laboratory that's not kind of the laboratory that we're all used to, where we sit and look at benchtop things. That's not that that's not good to do. It's good to do, but this is actually one at full scale. So students, particularly engineering students, can get a chance to see how this could become a teaching laboratory for them too. And another way for workforce development, which is a big issue these days, with creating a geothermal workforce that could actually take over some of this. We have high gradients in this region for this particular part of the country. We can do this on Cornell-owned property. We can utilize the existing infrastructure, and we've got a fair amount of drilling experience in the region, particularly in that range of 2 to 4 kilometers. So now we come back to take a closer look at this. This is at 3.5 kilometers, closer to where we're talking about. And again, this is that Appalachian Basin. We're going to that level. I think you should see Cornell there. You could put your own location on here anywhere. You're fortunate that you don't perhaps live in northern Minnesota where the gradients are even lower. So here's what the data look like. So this is a schematic here of the Appalachian Basin. What this represents, there's New York, Pennsylvania, and West Virginia. The dots on here are actually oil and gas wells drilled. You probably didn't realize that New York State was the first state in the country to produce natural gas. Even though they have a moratorium on it now, it's kind of interesting that they were the first. We've drilled, this graph represents data that we could extract from the archives that have been saved of about maybe 20,000 wells that have been drilled, and some of them are pretty deep. These are over 600 meters. Some of them are very deep. This goes from 600. This is less than shallower, less than 600 here. These are between 600 and 1,000 meters. So you have a fair amount of data. There are several that go much deeper than that, but unfortunately, none of them were right close to Ithaca. Although we had wells nearby, they were still a fair distance away. So you can do the best you can in taking that data and trying to interpolate it. And there are a couple of different ways. You could predict what the mean temperature would be at, say, 3.5 kilometers. Or you could find the regions where the temperature would be at 80 degrees or so. Either way, and Ithaca's up here again somewhere, you're still going to have to drill an exploration well. So this kind of takes us to what we've been trying to do at the campus. First of all, designing the system and creating this, and this is what we've been working on. We drilled this single borehole. Doing this well pair experiment, which is in front of us right now, and then eventually building up the entire infrastructure needed. These two projects are primarily being run by facilities with a lot of input from the faculty and students as advisors and participants, but a lot of this work was all done by people in the College of Engineering with some support, obviously, from facilities. But this shifts over to a much more Cornell-centric project. And we showed this earlier. And again, I want to give you some examples of how we're doing research in this area. So there's a fair amount of work that goes on above ground. A lot of it has to do with these augmentation for heat pumps that I'll show you in a minute. The other is the connection to the district energy system. What's the best way to do that? We have various temperature loads. Some of it's really high temperature, sort of sterilization temperatures for health purposes and things. Others of it is really low temperatures for the greenhouses on campus. So you have in dormitories as well as laboratories and buildings. So you have the ability to cascade that energy use, which helps out. And we have to do a fair amount of life cycle and techno-economic analysis. Ultimately, not to get so much at a levelized cost of electricity, which is usually what you see. This is a levelized cost of heat. And so below ground, there's a lot of stuff happening, right? Well drilling and completion, geologic and geophysical characterization, reservoir development, thermal and hydraulics of energy capture. This is where courses like 1050 and things like that could be pretty important background for this. And also the ability to use tracers, which is what's been an interest of mine for a number of years, to actually manage and control and understand how these reservoirs are actually behaving. You have no visual access to this experiment below you at 3 kilometers. You have to infer this from how fluid is flowing through the ground, what its temperatures might be, and what its residence time is. So we're trying to use that data to help us. So I'm going to say a couple of words about those areas. So the first has to do with this above ground activity. So what you can envision, and there have been a number of alternatives that Cornell has looked at, including a small modular nuclear reactor, which would probably not fly very well in that part of New York State right now, but clearly could provide all the district energy we needed. And the cost of that and the availability of it at that 2035 timeframe was certainly unreasonable. But what we could do is drill a lot of shallow heat pump holes, probably the things that you guys have heard of, except it would take about 10,000 of these to do it. These are only 500 feet deep. So they're using essentially near ambient temperatures, not stuff at 80 or 90 degrees centigrade. So the coefficient of performance, which is really the ratio of the amount of heat you're getting per unit of electricity you have to put in, is obviously an important figure. You want this as high as possible. If we were to use air source heat pumps, the kind of popular thing that's being installed, in the winter heating load, which is when we have this, we'd be talking about a COP of 2 or less, not very good. If it's really cold, the COP will probably be 1 because it'll just be direct electricity conversion to heat. But if we went to a geothermal system, which would, the logic of this gets pretty iffy here with the infrastructure you need to do that. Where do you put all those wells? How do you interconnect them? How do you control them? They have to last a long time. You could do it for small installations. I have this in my house, but that's one dwelling. We've got lots of buildings lots of complicated energy use on the campus. So, but if you do that, you get a big improvement, a good factor of 2 or so. So you get more value out of that electricity, but it's still a lot. But if you think about a way to integrate this, what we'd like to do, here's the district heating system. So you take fluid and supply it to the heat supply in this district energy system, and it's returned to you. But it's returned to you at a relatively high temperature because it can't go too low. So can you take advantage of this? Well, one way is you come out of the ground here with whatever it is, 80 degrees or so, and then you go through a series of these heat pumps, all of which have a relatively small lift because you're running them counter current. And the advantage of this is that helps this out here because we can essentially use less flow coming out of here to get the same amount of energy that we need. But more importantly, we can put stuff back in the reservoir at a much lower temperature. And that allows us to get more heat extracted per unit circulation. So it really saves on the number of wells you need in the circulation. So it enables active reservoir management, significantly improves and lowers improves the economics, lowers this levelized cost of heat, and it gives us a way to kind of see whether this might work with a campus. So here's some of the comparisons. So we looked at a couple of different reservoirs that we saw in drilling that first hole. These are in dollars per million BTUs, typical way for how you might compare it with natural gas. This is in the range of $5 to $6 or so, very affordable in today's markets. And if we were to do this without those super heat pumps, super COP heat pumps, thermal storage, and biomass peaking, we'd be talking about higher numbers, much more like it would cost if we did it with natural gas. And this is at commercial rates for natural gas, too, not like you get at home, okay, because Cornell has a very favorable rate for that, but it's still more than this. So when the campus looks at this and when the administration looks at it, they say, well, this could work, but we have to prove that it works, right? So you've got this risk at the front end. So heat pump integration has been a big plus to that. So the other findings of this, integrated heat pumps, improvement in the district heating system, making it more efficient. Peak heating using RNG is one thing, one option we're looking at, using the ag and food waste. I'll show you that in a minute. And then reasonable productivity and lifetime of these systems. So I told you about Cornell having cows. This is one of their barns. I guarantee you that the food that these guys are eating is better than what you guys consume because these are real producers. They have to function. They're like athletes in a sense. And this is an example of I think this is at the vet school barn where they're using it to train veterinarians, but they have a big animal science facility several miles away that we would also take advantage of that. So if you take the manure from that and you combine it with the campus food waste, which we have to do now anyways because of a new New York State law that's requiring you not to put it in a landfill if you produce more than 2 tons a week, and we certainly do that on a campus of our size. So the idea would be to go to anaerobic digestion, which is well-known technology, which converts the biomass, roughly about 50% of it gets converted, and about half of that gas that's emitted, the biogas, is CO2. So we further could augment that by using a process called biomethanation, and we would use renewable electricity when we have it available and run that biomethanation plant. That almost doubles the amount of methane we get out. Interestingly enough, there's a huge credit for putting renewable natural gas back in the pipeline. It's almost too good not to do, right? And so from the standpoint of cost recovery, this would more or less pay for itself. We're adding some other features here which tie into some of the research in hydrothermal conversion because we'd like to convert that digestate, the liquid digestate that comes out that hasn't been converted, into more products, including hydrochar, recover some of the nutrients, and maybe bio-oil or something like that, all of which would have market value, but not to the same extent that this renewable gas has. So that takes care of that. Now, in a few minutes, and I don't have many minutes left, I don't know when I'm supposed to stop, but we'll keep going for a while, right? It's sort of normal 1040 lecture, right? Right. Okay. So I want you to think about the engineering side of this for a minute. So I talked about this earlier. We need importantly high temperatures, lots of rock volume, lots of surface area. So and you also don't want too much resistance within this system because you have to pay for that because you're pumping the fluid around wells. So you have to live with what nature has given you. The reason the heat's there in the first place, thermal conductivity of this rock is low. It wouldn't be there. The planet's old, but it's also huge. And so at those depths, we're talking about a lot of stored thermal energy, and figuring out how you're going to get it out means you have to kind of surmount the inherent limitations of a low thermal conductivity, which reflects itself in a low thermal diffusivity. So just make a simple thermal penetration calculation and imagine a two-dimensional representation of a complex flow. Here's a fracture or something. There's rock on either side. We're extracting the heat from it, and we're going to do it with these properties: 2.5 watts per meter K, a density of about 2,500 kilograms per cubic meter, and a heat capacity of about 1,000. That's typical for the rocks we'd see. And so you end up with something like 10 to the minus 6 square meters per second. You can do the math, and you'll figure out that in 5 years you generate a penetration wave of about 10 meters or more back into that rock surface, perpendicular to the flow. And even at 25 years, plenty good enough to, it's only 25 meters. So what this tells you immediately is you need a lot of surface area to make this work. And so you can look at a one-dimensional representation, and I promised you I'd only show you one error function here, but this is a clearly simplified problem. Uniform flow, transient conduction back into the rock, starting with initial uniform temperature. And the expression of this, and the key variable here, that this thing depends on. Here's the properties of the rock. There's time. That's the area, the surface area of this domain that you have over that fracture surface, and there's the flow rate. So minimizing the flow rate's bad for the economics, accelerates the drawdown. Maximizing the area is good for everything if you can do it, but it's not so easy to do. So one approach, which was started long ago, long before we even thought about this up at Cornell, was to go to multiple fractures. This is clearly an idealization, but it really changes the thermal characteristics, because now you're generating, in this particular case, 3 times the area with the same flow requirements of that well pair. And so if you carry this out further and say, well, this is with 5 of them, what would happen over time? Well, you'll see, if you assume uniform flow, very idealized to start with, that you'll just see that temperature progress through this, but it's not going to get there right away. This is after quite a period of time of production. So we've looked at this you can get a simple graph that kind of tells you what you have to do. So we plotted well separation here, and this is in meters now, so it's a log scale. So it tells you how far apart that injection and production well is. And then we plotted initial thermal power here. So if you had 10 megawatts, just for example, you need 5 of these well pairs to do the whole campus. Not 1,000, not more than 1,000, 5. So it changes things. Of course, they're more expensive wells. This is the flow rate in kilograms per second. So you're in that range that we've achieved hydrothermally. And this is the prediction of what the thermal decline would be over a period of time. You're mining the heat out faster than it's going in there, but you have enough surface area to kind of compensate for a good portion of that. If you flow at even a lower flow rate, the economics look bad, but you can sustain it forever. So it's really a trade-off between what would you accept in a reasonable drawdown. So the current focus is this is what the well pair would look like at Cornell. We would drill long laterals, create multiple fractures. There's some interesting work going on now in the American West where they've done this using sort of the same kind of technology that's being developed for shale gas and shale oil production, where you multiply stimulate a whole region. But these distances now are like 100 meters or 200 meters, things that could be achieved, because getting long distances over a single fracture is very hard to do. So you go back to this diagram, and if you look at this, here's one. This would say you need something around 300 meters, but if you envision the kind of flow through there, an injection region, production region in each hole, it's feasible that this would work. This is what we have to actually do. So how is Cornell going about this? I'm going to probably skip this now because I don't have enough time, and I want to show you the well. We might come back to this at the end if you have questions. This has to do with a kind of really interesting thing on active tracers that we use to control flow and understand flow in there. Lots of material science in here, some things I'm sure would be of interest to you. And this involves a very large study with a lot of people involved from different departments. So, in fact, you can see some of them here: material science, several people in chemical engineering, as well as in earth sciences. And so let me get to what Cornell's trying to do. So this first well is what we call CUBO. I didn't come up with this name, but this is the Cornell University Borehole Observatory, because the earth scientists view this, even if this thing fails, we've got an experiment that not many other campuses have that could be used going forward. But so it's relevant certainly to the Earth Source Heat Program, lowers the technical risks, uncertainties, mitigates the potential hazards and environmental impacts, but it's also relative to geoscience research. So it's got this sort of double benefit if you look at it. And we can use a well like this, an exploration well or an observation well, to monitor the performance of this well pair system we're talking about. So it would be shown here like in yellow, and then the first well pair would be essentially very nearby to that, so we could actually look at that condition. So this is the drill rig on the Cornell campus, probably something you wouldn't have here often at MIT, but this was on an abandoned parking lot. To mobilize this rig takes about 80 18-wheelers to pull it in. Takes a pocket exchange of about $2 million to bring it to the site, even though it was just a few miles away. And they told us they would set it up in a couple of, maybe 3 or 4 days. It took 2 weeks. And we also did this during the pandemic, which is a terrible time to do anything, particularly because of the costs and supply chain issues that we had during that period. So everything was double in terms of cost, time, money, people. But this was done by a very professional drilling company that came up from Pennsylvania. And so here's what the geology looked like. A lot of our sedimentary geologists were very interested in this. We have a lot of information, but no one had ever drilled a hole here. So we could validate a lot of all the cuttings were taken. We took multiple cores. We wanted to take more, but it was so expensive. Lots of sidewall cores were taken in the lower section. So here's where things get very interesting for temperature. Very complicated casing program, extremely expensive. But we did it all and got down to that depth of about 3 kilometers or 10,000 feet. And that's the potential region that we're going to try to develop for heat extraction. So we know the temperatures are warm enough. This is an example of early testing of the temperatures. So, and again, this is not to the bottom of the well. That was only as far as we could go because there was some damaged material in the hole. We didn't want to try to push the temperature measurement any deeper. So it clearly led to temperatures in excess of 80 degrees or so at the bottom. A lot of additional work went on to sort of map the behavior of these, understand the geologic conditions, fiber optics being installed and trying to look at stress changes that occur. A lot of imaging that went on with microprocessing and other things. So that work is perfect for master's and doctoral thesis in earth sciences as well as some of the other. And we have this sort of smart tracers program that involves a number of us in the longer term issues associated with reservoir performance. And so I'm going to, these are the takeaway messages. Let's get these in and then we can see what people want to have questions. We can come back to it. So the first is, this is the living laboratory for sure, for on-campus research at scale. That is not always to do, and so Cornell's to receive a lot of credit for that. Not only that, they made a huge investment. So when we initially proposed this to the Department of Energy, under one of their funding opportunity announcements, we thought we could do the whole thing for $7.5 million. But when you tried to do it during that period of time, everything was double. The acquisition of casing, the drill rig day rate, the mobilization charge, et cetera, and a bunch of other things we didn't anticipate that I could get into if you're interested. So, but Cornell stepped up to the line in the difficult period and covered the extra cost for that. So we didn't attempt to quit halfway or try to attempt to get more out of the DOE. We reached these temperatures for sure, and we identified several target regions. So in a sense, that CUBO well was quite successful. But to go further, we're really talking about this kind of investment because now you have to drill long laterals, and none of those costs have come back to where they were pre-pandemic for sure. And that's what we think is a reasonable number when you combine it with, with the stimulation requirements and the casing and long laterals that would have to be drilled to guarantee we have enough surface area. But if we can do this, we think that kind of demonstration, Cornell is a land-grant institution in New York. I think it was the first one in the US too. But this could have the kind of impact that would show people that this actually could be done and might help to make the kind of transformation that I think is going to be needed if we're really going to get to low carbon in those heating-dominated states for sure that we have many of. So let's quit there for now. And we're almost on time, right? But I'll take some questions, and then if anybody wants to hang around, I'll show you some more details on our tracer program.
So we will open it up to questions, and we'll pass the microphone around. I'll start. Where's the extra $40 to $60 million coming from?
Well, we were hoping you guys would write a check for us, Chris. Okay, so that's a really good question. So there is we've responded back to a recent Department of Energy second FOA, okay? But unlike reality, they want a full-scale demonstration, and they only have 14 million. So that's not going to work. So we still responded to it. We told them, here's what we could do, and we'll see how that goes. You know, it was due just a few weeks before the election, and we, of course, haven't heard anything, but I suspect that there will be some re-examining that in general, because nobody could do it for that. You know, we're not alone here. It had minimal cost share. It was about 20% cost share. We were handling that as well in our submission. But most likely, it's got to be a big participation from the state of New York. They claim they're really interested in this, but they're funding a huge amount in solar and wind. And now they've gotten into the air source heat pump game, which seems to me a losing cause when you look at all the electricity they're going to need and their loss of their carbon neutral electricity when they start shutting down nuclear plants. So it's kind of difficult to see how they're going to do it unless they really get involved with something like this. So we hope that will change. The rest we hope will come from partners. So, you know, and they might have a vested interest in one company. I don't think I'm speaking out of turn. The company that developed the district geothermal system in Paris and expanded it is the ENGIE company. And they know how to do this, but they're really dealing with a very different geologic setting. They have a warm aquifer that they have full access to, fully characterized. So it's not the same thing as what we're talking about with the EGS, but it would give them some interest. And they do a lot of work on energy development in the U.S., so that's a possibility. Also, the companies that are interested in subsurface characterization, Schlumberger, Baker Hughes, they could see a market potentially down the road, because you need technology to characterize the formation. So those are potential partners. Nothing to write home about yet, but that's what the effort is right now, for sure. Does that cover it?
Yeah.
Okay. Yes.
Hi, thank you for your presentation. I really love the emphasis on student engagement and using campus as a living laboratory. My question is, for campuses and professionals who are not yet familiar, what recommendations do you have to educate people such that they consider this design as part of decarbonization planning? So for context, I'm working with a couple of students and alumni to have MIT consider thermal energy networks, which I think is very similar, if not I think a different word than I've heard you use today with the engineered thermal systems.
Right. So that's a great question. So you can't do everything for everybody, but one thing we did learn in the pandemic is how to do things with distance learning, right? And so one option might be, and Dr. Peters in this room will know this well, we started a course a long time ago called Sustainable Energy Systems. I think Professor Green is involved with that too, and others perhaps in this room. And it sort of hybridized when we got up to Ithaca, because we found that students really wanted to know more. There's only so much we could do if we looked at everything at once. So we did the sort of front-end course, but then we broke everything into modules. There were a number of students who were really interested in energy storage. I was talking about that earlier. That has huge interest right now. Batteries, thermal storage, pumped water storage, a lot interested in solar and wind, but there was a group interested in geothermal, so we teach that. And what we could do, and we've thought about this, is to get into a distance learning. These are only 12 lectures or so, but they provide a lot of information, and they give students some appreciation, whether they're coming from geology or from engineering, to kind of understand both of those disciplines. And I think it's worked well. We've done it about 11 years now, and it took, the registrar hates me, okay, because we do things broken up into a semester, and they're usually one-credit modules. I think maybe you've accomplished some of that here now, I don't know. But it's across the whole university, not just engineering, so it's one way. But you got to spend time learning the technology, yeah. Go ahead, Bill.
Jeff, can you say more about the opportunities for in situ diagnostics? You mentioned
Okay.
tracers.
Right, tracers, yeah.
Just to finish the thought,
Yeah.
one way to think of what you're doing there, these are like very sophisticated heat exchangers in which there are also reactions.
Exactly. Right,
And so, are there some additional diagnostics you'd like to have, perhaps
well-
from our material science people or
Exactly,
electrical engineering
right.
friends that you don't have now?
Well, we're doing part of that, but I think it's a wide open field. So let me go back a little bit. This will take a minute or two. I didn't pay you to make that question, Bill, but I'm glad you did it. Okay. So you're familiar with some of the early work we did, but there was a lot of effort put into what we'll call conservative and inert tracers. They are very much like you would measure the residence time distribution in a packed bed reactor, something like that. But they don't tell you anything about the thermal change inside the system. So then we started looking at thermally reactive tracers, ones that would respond to the thermal field as well as the hydraulic field. Not an easy problem to invert, but still gives you some additional information. In addition, along the way, for other reasons, there were some engineered carbon nanoparticles that were incredibly good for used as inert tracers. But they can also, these were fluorinated, if you will, with essentially things that could be optically activated. So we could study these at incredibly low concentrations. One of the difficulties is what's going to be the net recovery. There's a real long residence time as well as kind of a distribution of shorter term times within a fracture. But the most interesting part, Bill, is this last one here, where we're now developing with the material science department microgels that are thermally responsive. And these things, we're calling them smart tracers because when they get cold, they expand. And what you might want to have a tracer expand is to shut off short circuits that occur in that fracture system. This is an example of a short circuit here. This was a uniform temperature to begin with, and then when we actually heated it up, this is a shallow reservoir up in the northern part of the Adirondacks that we can test this. Actually in some of the same rock, but very near the surface in that geologic region. And what happens is this thing tends to have a flow path due to the geometry, the natural geometry that's there. So what you'd like to do is to shut that off after a period of time and circulate the flow to other regions. So that's what the hope is here. And the concept of this, we're using a hydrophilic and hydrophobic type tracer that was actually, I think, originally invented at MIT, like a lot of things, a long time ago, for different reasons, not for this application, that swells when it gets cold. And the temperatures that this has been looked at are in just exactly the range we need. At the injection region, it gets to temperatures that are pretty low because it's cooling off, right? So you have to be careful that you don't plug up the well going in, but if you can get it in there, because there is a kinetics associated with this swelling process, we think it'll work well. So a lot of work now. This was Tanaka's work back in the 60s when this was going on. I'm sorry, the 80s. And then a lot of follow-up papers that went on with this, but it's never been used in this application. So you get a huge change in volume. This is an example over that 30 degrees C or so of about a factor of 100 or more in terms of volume for that swelled particle. So in principle, this could work, Bill. We got a long way to go.
But
Yeah.
the tracers, is there a way to get them to report during their journey in situ, or are you measuring the integral effect, just like measuring
Well,
an RTD?
we certainly think that, like, if you took that carbon nanoparticle, we've been also talking to Professor Strano about this because he's interested in this as well, that might be a real opportunity for, sort of engineered, molecularly engineered particles. But the carbon nanoparticle might be the best way to go because it's got a pretty stable core, and you could somehow functionalize it in a way that it would respond to temperatures, but it's still not going to be easy. We still need to do both flow management as well as flow mapping. So hopefully that will work well, Bill. But I mean, this is research going on now, and there's about 6 of us involved with this with a fair number of faculty, and DOE is supporting that directly. And again, the idea, if you just envision, this is a model now, 1,000 meters or so. So it's a hugely big fracture. Again, we're just looking at this idealization. There's the injection and production well. And this is an aperture field which more or less represents the aperture field we saw in this mesoscale site that we have up in the Adirondacks, this Altona site. So we said, what would happen if we had that at that larger scale? And of course, this is the short circuit, and if you put in these reactive or smart tracers, you can change that flow pattern, and it really changes the output. So this is without those tracers present over that period of time. You get a huge amount of, so this is at 200 degrees, much different temperatures, but it's all relative, right? Again, with that kind of flow rate, that size, and this is if you had that kind of flow control. So the outcome could be large, but again, we have to do this. So we're trying it out both in the field on a smaller scale, on a large laboratory sort of base of these are actually granite slabs that we've developed, and that's underway right now. So talk to me in about a year or so, maybe have a little more data. But we want to do it in a real reservoir. But you have to make a lot of these microgels. So this is a production operation too. We can't just do it with a kilogram or two. So the production of this at large scale, is it monodispersed? Is it polydispersed? Can we keep them stable for long periods of time? All kinds of great questions. So I know it's a long answer, but I took the rest of the talk then, right? So thank you.
So we will we'll stop the Q&A there. I think Jeff will be around for a few minutes to
Sure.
answer more questions. I get to make now the formal presentation of the Hottel Bowl. You have to come there so people can
I
see
see.
you. So it really is a pleasure to have Jeff back. I left out the part how when I was a junior faculty member, we shared an office suite. And as you might imagine from hearing his talk, that was a lot of fun.
And we have Glenn here. She's responsible for probably all of us.
There
still
she
being
is.
here, right?
Exactly.
Right.
Thank you very much for coming,
Thank
Jeff.
you.
We really enjoyed your presentation.
Thank you so much for the invitation. It's been a pleasure. This is great.